This has been a really incredible year for Canonicle. I released Canonicle last May, and the following day, Terence Tao used Canonicle as a part of the Equational Theories project. He uploaded a YouTube video garnering tens of thousands of views. And in the following months, I released many new subsystems for Canonicle. I released a structure editor for Lean, which is a graphical user interface to construct terms. I introduced the ability for Canonicle to use the simplifier as a part of its reasoning. I introduced a monomorphization procedure that allows Canonicle to reason about type class instances. And I released a new subsystem called Destruct to help Canonicle reason about structure types. I then gave a talk at ITP 2025 where I introduced the world to Canonicle to great enthusiasm. And the first question that I received upon giving this talk was about scalability. How are we going to be able to take this system, which has clearly demonstrated that it can generate short proof terms of simple statements that have short proofs, and use it to really automate larger scale lemmas and theorems in a broader project, right? How are we going to make this practical for whole proof automation? Well, there's been a lot of people working in this space, so maybe what we should do is what everybody else is doing. We should generate it with an LLM, right? There's plenty of companies out there working on generating these kinds of proofs, which are tactic-based proofs in Lean, as text. And I think this is a bad idea. And I'm going to explain to you why I think this is a bad idea. First of all, it's very brittle, by which I mean that tactics change very much from version to version in Lean. And also the lemmas and the theorems in the mathematics library change from version to version. And so a system that's been trained specifically for one particular version of Lean is not going to be able to adapt to these kinds of changes. Furthermore, if you have your own project that has its own lemmas and theorems and its own tactics, it's not going to be able to use those tactics in reasoning. We've seen this in particular. These systems can't use Canonicle because Canonicle doesn't actually show up in a final proof term. And so the systems are not fully taking advantage of the tactics that are available to them. Furthermore, the proofs that are generated by LLMs tend to be very verbose. And the reason is quite simple. We penalize the language models for generating a tactic step that does not compile. And so the models become incredibly cautious. They write proof steps that don't do very much but have a high chance of compiling and lead to proofs that are not very they don't have very much insight. They don't communicate very much understanding. And generating all these tokens is very expensive, and we have to use the biggest frontier models in order to do this reasoning because the system needs to be able to predict the behavior of Lean tactics. Predicting the behavior of Lean tactics is very difficult because tactics are extremely complicated and inherently unpredictable. They're meta-programs written by many different developers. And attempting to train a model at this seemingly impossible task requires a lot of compute, and it's very expensive. I mean, imagine being tasked with proving this theorem, and you have access to a text editor, but not the Lean info view, and you have to write a proof that compiles. You're not going to succeed. And so somehow we expect the models to be able to succeed at this task. And inevitably, when they fail, we then have to backtrack and generate many reasoning tokens to explain why the failure occurred and what should be done instead so that we can suggest an alternative. And all of these tokens, again, for the frontier models are very expensive. It's amazing and a little ridiculous that we live in a world now where you have to pay for proofs. And I'm going to argue that it's entirely wasteful. We're doing a lot of things with the machine learning models here that can be done entirely using search-based methods. I mentioned before that these LLMs are not able to use tactics like Canonicle and exact question mark, library search, these things that replace themselves with the correct proof in the program, but it even goes deeper than that. Imagine that an LLM recommends a call to grind, the new closer tactic from Leo de Mora. If the LLM suggests a call to grind, you could have just called grind before the LLM suggested it. And if it succeeded, then you're done. And if it didn't succeed, then there's no need for the LLM to generate such a call to grind because you know it's going to fail. right? There's no sense in having an LLM generate a call to the simplifier, because either the simplifier works and it simplifies the goal, or it doesn't simplify the goal and you shouldn't apply it, right? And so there's no need for the LLMs to be generating these sorts of things. I mean, at a high level, there's only a handful of really important tactics in MathLib. Why not just try all the tactics and see which of them work and which of them don't, as opposed to having an LLM make a recommendation as to which tactic to do at each step, right? And so that's kind of my fundamental idea here. And I'd like to make it actionable with a new user interface that I call typewriter. So I'm going to show you this new user interface for writing lean proofs that entirely forgoes the tactic interface. So let me show this to you. So let's say that we're proving something of type A. The typewriter system opens up this user interface in the info view here, and you're presented with a text box where you can write an intermediate statement or a type. So in this case, I'm going to say, okay, we're on the goal of proving A, and I would like to prove B. So when I hit enter, what's going to happen is now we have two goals. So if you can look up here at the top, we now have two goals. The first goal is to prove B, and the second goal is to prove A from B, right? So what we've done is we've introduced a cut in the problem, right? We've separated it into two sub-goals. And I can do something like C implies D. Now we have three goals. So the first is to prove that given C we have D, so it automatically introed the C. Then we have that C implies D gives us B, and then we have that B gives us A, right? So we're progressively breaking the goal down. But here's the cool thing. I can take a goal like this, and I can suggest the type, 2 plus 2 equals 4. And when I hit enter, another goal isn't created. This statement is automatically introduced into the context. Now, why is it introduced into the context? It's because the automation was able to close that goal automatically. So in the background, we're running the tactics. We're running grind, we're running simp, we're running canonical, all of these things in the background to fill the goals when they can be filled by automation, right? As another example, I can say false, and false won't get proven immediately, but if I click this next one, you can watch it disappeared. If you saw that really quickly, it disappeared immediately. Why did it disappear? Because false implies anything, right? And it was able to discharge that reasoning. So if I call typewriter on a problem that can be solved by grind, it's immediately able to produce the call to grind. If I have something that's solved by simp, it's able to immediately solve it with simp. And if I have something that can be solved by library search, so in this case, a similar theorem is already in the local context, it's going to be able to solve it with library search, right? So this is all happening automatically behind the scenes with the typewriter interface. And it means that as the user, you can just focus on breaking down the problem until it's small enough to be discharged by the automation. We're running all the automation behind the scenes. You don't have to know the tactic language. You only have to know the term language. So to recap, there's two languages in Lean. There's the term language, which is rather well behaved, and there's the tactic language, which is not well behaved. But with this system, you don't even need to understand the tactic language in order to use it. Second of all, it never misses a successful tactic, right? If there is some way that grind or simp or one of these tactics is going to close the goal, it's going to find it for you, and you don't have to do any further reasoning. And furthermore, it's not going to recommend a tactic to you that doesn't actually close the goal because it's trying them in the background for you. And with this system, the tactics can improve and change and adapt independently of the user's ability to prove theorems. In fact, the more tactics you have, as opposed to things getting more complicated to prove, they actually become easier to prove, because the more tactics you have, the more complicated those tactics are. It doesn't matter. It's more likely to solve the sub-goals, and so it's easier for you to justify your argument, right? And you justify it just like a mathematician does in a math paper. You say, this is true, therefore this is true, and when the system doesn't understand, you come back and you give it more information. And I'll note that this is only possible because Canonicle has completeness for dependent type theory. If you don't have a system like Canonicle built in, then there will be some goals that no matter how finely you break them down, you won't be able to prove them. All right, so what are we going to do with this system? Well, it's my great pleasure to announce today Canonicle 2. All right, so what is Canonicle 2? So Canonicle 2 is a regular offline tactic I used to joke about how much I should charge for Canonicle, but now that's not so much of a joke anymore. But no, this one is completely free. It runs on your machine. And it produces proof terms, just like the original Canonicle, with calls to the simplifier and new to Canonicle 2 calls to grind. So how does Canonicle 2 work? Well, it's two systems in one. On the CPU, we have the tactics running, all of these different tactics in Lean. And then on the GPU, we have a language model interacting with the typewriter interface. So the language model is not responsible for producing tactics. It's responsible for producing intermediate statements, right? And these intermediate statements are converted into let definitions or have statements in the proof that's generated. So you get proofs that are hierarchically structured. You have statements, and each of those have statements, and so on. And you get these nice proofs as a result. And I'm going to claim that it's completely slop-free. And the reasoning, my justification for that, is that the proofs, the tactics, are not slop because they're not even generated by an LLM. And the intermediate statements are not slop because we don't penalize the model for generating a statement that doesn't immediately lead to a success or a failure. So unlike the tactic case, where if a tactic fails, we penalize the model, in this case, we want the model to come up with ambitious have statements that break down the goal into large pieces, as opposed to making all of these small statements that don't take you anywhere. All right, so let's actually look at how this works. So I've got some examples loaded here. So I'm going to start with this simple example, which is an identity about maximum on a linear ordered group. And it's just being able to extract a negation out of a maximum. So it's saying that the max of a negation of a and 0 is negative a plus the max of a and 0. Now, why is this true? Well, intuitively, you can sort of break it down into cases, right? Either, a is less than or equal to 0, or a is greater than or equal to 0, right? That's kind of how I conceptualize this sort of argument. So let's run Canonicle 2 here and see what it thinks about this. So on the right here, we'll see the proof being generated, and you'll see that the model has suggested a have statement. And now the model has suggested another have statement, and both of those have been closed by simp. And before we know it, so here's the proof that we've generated. So what does it do? It breaks down the problem into two cases. It breaks it down into a less than or equal to 0 and a 0 less than or equal to a case. Each of those were discharged by the simplifier, and then grind was able to close it off at the end. Yes?
Can I ask a clarifying question about how the typewriter interface works?
Yeah.
So is it always going to, like when it's successful, result in a single tactic, like simp all, or is it going to possibly have many tactics come together?
So there are sort of two categories of tactics. There's tactics that do simplifications, or like that progress you towards a normal form, and then there are closer tactics that actually close the goal. So there are some cases where a simplification tactic followed by a closer tactic will be applied. These simplifications will always be applied whenever they're successful, and once a closer tactic succeeds, then that will be the one that maybe finishes the goal. So sometimes there'll be two tactics, but generally one. Yes?
So it's the LLM that guessed to split on 0?
The LLM generated these types. So the LLM is responsible for writing the intermediate statements that break down the problem so that it can be solved by automation.
Got it. So there could be slop, right, in the sense that it could be like, oh, less than or equal to 1, oh, and then we split it again, right? Like there's no guarantee that there's going to be an elegant split like the one you found here.
I guess that comes down to how you train a system like this. But if you have a useless split, we wouldn't recommend that split. And in some sense, the typewriter interface guarantees that there is no unnecessary split, as in every split was necessary in order to solve, like if there was a way that the automation could close the goal as is, it would just close the goal as is. But it was not evidently able to do so, and so therefore more clarification was needed in order to close the goal past that point. So there won't be any unnecessary steps. Like every have statement will itself be necessary, if that makes sense.
But there could be a much more efficient set of paths.
There could be a totally different approach to the mathematics, and this is the case, for human proofs as well. I mean, there's many different ways to skin this cat, but I think the ways that we'll see here, and we look at this proof, and I think it's very idiomatic, and I hope the examples that I show will sort of demonstrate that because the model isn't generating tactics, we're getting something that's much more akin to a reasonable breakdown of the problem.
I just had one other brief question.
Yeah.
Which is, what's the LLM that you're using?
So this is a custom fine-tuned version of Qwen 3.5. And so I'd like to thank Sean Wellick and Andre He and also Frederick Pu, who's an undergraduate at University of Toronto. They've been a great help on the language modeling side of things. And so we have our own data, we have our own methodology for training. And what you're seeing here is actually just the start. We haven't done any expert iteration. We haven't done any rejection sampling or things beyond just basic fine-tuning. So we have some very exciting plans for how to make this much better. But I'm showing you a little sneak preview of what this system is capable of. So let me show some more examples here. So I found this statement here, which I admit I'm not fully familiar with all of the algebraic ramifications of these inequalities, but we have something here that's simultaneously a lattice and a commutative group and has monotonicity properties, and this evidently is a important lemma to be aware of. But regardless, I'm not exactly sure how to prove it. So let's take a look how Canonicle 2 breaks this down. So it's suggesting a couple inequalities that seem to be useful for proving it. And there we go. So let's take a look at what it did. So we're trying to show that the join of these two is less than or equal to this division here. And it looks like it's broken it down into the two cases of showing that each of these components are themselves less than or equal to the right-hand side. So Canonicle fills in this part here. It looks like library search maybe was able to find the important cases for each half. And so it broke down the problem in what I think is a sensible way based on the success of it. And we get this proof that I think is pretty nice. All right, so let me show another example here. So this is a pretty simple case, but I want to show induction. So here we have a proof that f of x is the identity function, and we want to show that when you iterate f using this iterated function syntax, that it's also equal to x for any n, right? And so how do we approach a proof like this? Well, the first thing we might want to do is do the base case. Okay, that's nice. And then we might want to do the inductive step. So here the LLM is recommending the inductive step. And then Canonicle finishes off the proof with a recursor on the natural number and is able to do the final induction, right? So there is no individual tactic that can do induction except for Canonicle, as far as I'm aware. And so what we're showing here is that the model is able to solve the two relevant components, and then Canonicle is able to bring them together in order to construct an overall inductive argument, right? All right, I'll just keep going, showing more examples. So here we have that if a prime is even, and let's see what evenness is defined as. So it must be that there exists in R such that A is equal to R plus R. So that would be the additive version of this. And then somehow we have to show that if that is the case, then P has to be equal to 2. Okay. So let's see what this system is able to come up with. Okay, so this one appears to be pretty simple, but it's rephrased the evenness of P to be that 2 divides P. Okay, and that's somewhat different than P being able to be expressed as a sum of something plus itself. And the conversion is handled by grind here at the bottom, and then this lemma is handled by grind as well, using this statement about primality. Yeah, about division of primality. Yeah.
Chase,
Yes.
which component selected that argument to grind?
So we have premise selection running, and this is the premise selector created by Sean Wellick's group and Thomas Zhu. I'm very interested in shopping around for different premise selectors, and I'd like to see, I'd like to see development in this area. But so there's various different components. We have the language model generating the statements. We have an embedding model doing the premise selection, and then we have the tactics running on the CPU. Yeah. And then we can round this out by showing that if it's odd, then it has to be greater than or equal to 3. And this uses actually the previous theorem here to justify the reasoning. So it's able to, the premise selector is able to use things locally in the file as well. So yeah, I guess, I mean, I could keep showing more examples, but I think what I might want to do is just sort of round out the discussion with this thought that I've been having recently. I think we all first encounter proof as being sort of like a series of statements. You know, this is true, therefore this is true, and so this is true, you know, in a math textbook. And then we all learned about formal proof and how you can construct an object that is, you know, verifiably, formally a certificate of something being true. But in this past year, I've recently gone back to the initial conception of a proof as being a series of statements in succession. And I'd like to explain why. I think that a proof is fundamentally about communication. And I think that a term-based proof fails communication in two aspects. First of all, if I show you a proof term, you are no more likely to understand the argument as you were before I showed you the proof term. The only way you can be convinced of the argument is to actually look at the types at each intermediate step in that statement, to type check it and look at the term at every boundary, you know, what are the types at each point. And so it's in fact not the term that's communicating to you the proof, it's the types that are communicating to you the proof, right? If I showed you the types, that would be more convincing than showing you the terms. And the other reason that I don't think a term is a good form of communication is that I no longer believe that there is one true term language that everybody can agree upon. I think that in our own minds, we each have our own set of statements that we think are trivial and our own set of statements that we think require further justification. And we see that the same is true in Lean and Rook and Agda and all these other systems. They all have their own opinions about which things are trivial, which things are already in the library, which things are obvious, which things are solvable by automation, which things are not solvable by automation, right? And yet, for hundreds of years, you know, mathematicians have coalesced upon a language of statements, and they're able to communicate statement-based proofs very effectively, even when different people have different opinions about what is trivial and what requires further justification. And I think the typewriter interface sort of gives us an intuition as to why. So my vision is that the prover-verifier dichotomy becomes a more active enterprise. You have a more active verifier than you did previously. So my vision is that you have a prover that produces statements, and then you have a verifier that attempts to understand why those statements are true in its internal representation of terms, by which I mean it's producing the proofs itself, attempting to justify each step of the reasoning. And so the verifier is actively trying to understand what the prover is talking about, but when it fails to understand a particular step in reasoning, it requests additional explanation. It requests another intermediate statement that helps it see why one follows from the next, right? And so the typewriter interface shows a method of communication that's entirely based on explaining the mathematics as statements, and it's the responsibility of the system that actually understands the terms to create those terms itself, right? And the big picture here is that as automation gets more sophisticated, as we add more and more tactics for more and more specific areas, and as we have more independent systems that all need to communicate with each other, I think the way to do this is to realize what mathematicians have realized for hundreds of years, which is that a statement-based proof where one thing follows from the next is something that really transcends time. I hope to release Canonicle 2 this summer, although that's dependent on our ability to do more post-training. But I'm really excited about this capability and about this system, and I hope you all are just as excited as I am.
Statement-based proof, you mean for reasoning, is that right?
Yes, so I think one way to view what we're doing here, so I believe that there's sort of, I'm realizing this massive duality, right? Hence the large emphasis on two, right? I'm realizing this large structural duality, which is that if you're doing backwards reasoning, you basically have to use search because you're doing destructive steps that require backtracking and you have to go try something else. And so most of the directions you go down are wrong, and you have to basically do the traditional formal methods thing of trying a bunch of different things and creating a tree search and so on and so forth. But when you're doing, these cuts in the forward reasoning direction, there's basically no way that you can search for a statement out of thin air. I mean, every statement is a valid statement, and any proof that has a proof with cut is going to have a proof without cut. That's going to be easier to search for. And so it's my view that inference is necessary for generating types, and search is necessary for generating terms. And so it creates this perfect separation of responsibilities, right? I think that the reason that we are needing to use these very, very large LLMs that run on servers, again, this LLM that we're talking about here is running locally on my device. There's no internet involved. The reason that we're able to do so is that we're not overburdening the model with responsibilities that it's not fundamentally equipped for. Reasoning about the tactic language, reasoning about terms, reasoning about search, right? Attempting to do backtracking and all of these things. So yeah, and that's my response. I think that it's necessary to use inference for this particular task.
You mentioned that the first question they asked you at ITP was about how does this scale, and still the examples you showed are still all very small in terms of the number of lines. So yeah, I was wondering what's the largest goal in which you have tried this. Is there something, for example, where proofs are hundreds of lines and you have been able to close with this?
So I don't have an example of hundreds of lines proofs. I think the important thing to note here is that we haven't actually trained the system to operate inside the harness. So we've trained it on synthetically generated data that basically teaches it what the format is. So it knows basically what it's supposed to be doing. But we haven't actually done what I'm really excited about, which is reinforcing strong behaviors and punishing, bad behaviors and so on and so forth, to actually get a model that's designed to carry out this task in the harness. And so what I'm hoping is that this sort of brings about a new way, a new approach of the problem that allows you to go from, we require the largest models ever, we require, thousands, millions of dollars of compute, to something where it's if you choose very carefully what it is you need to do, you can get proofs that have, in this case, we've shown, a couple have statements. There are some where it's able to do, 5 or 6 or whatever that I've seen. But, we want to really bring this to a larger scale. And I think that have statements naturally lend themselves to this kind of reasoning because it's hierarchical. I mean, you work on one half of it, and if you're able to solve that one half of it and you're able to solve this one half of it, those two things operate independently of one another, right? And so, I mean, one question might just be, if we took a proof that Canonicle 2 succeeded on, and we removed one of the premises that it needed to prove that, would it go about proving the premise as one of the, and continue to write a longer and longer proof? So yeah, these are questions that we would want to investigate.
Another small question actually, does it have some ability to actually split into lemmas? Meaning if something's too complicated, for example, presumably if your halves are sufficiently complex, you want to kind of abstract them out of the context of the theorem you're in.
Yeah, I think that's, I don't have a particular opinion. I haven't thought about exactly what constitutes this have statement should actually be independent or something like that. But I think it might be somewhat of a stylistic decision. I'm not entirely sure.
Because you mentioned the premise selector can use things in local context, but can it use internal halves that are, for example, within a previous proof?
No, not within a previous proof, right? Yeah. That's isolated. So I struggle to understand, and I would be really excited about this, how to determine whether intermediate lemma is interesting. I don't know exactly how to tell. If we can do that, then we might have more than an automated theorem prover on our hands. We might have some automated mathematician, you know what I mean? So yeah, I'm very curious about that though. All right, should we get some cookies? Or maybe one more question.
I understand that you haven't trained the model as you want, but if you can, what would be the method you use to give feedback to the training?
So this is an interesting question. I think what we really want to avoid is giving some kind of reward that's this intermediate statement is good if it immediately gets closed by automation, or if it's identical to a tactic that automatically succeeds, right? Because that's how you get the proofs that don't actually break down the problem. They just try to greedily do things that succeed, right? I think what you want to do is you have two questions to ask. You have, is this have statement productive? Meaning, if I have that have statement, how's that going to help me? Am I making the problem any simpler when I'm going to that have statement? Well, I guess those are kind of the two questions. If I go into that have statement, am I more likely to be able to succeed with my automation and with breaking it down? And then once I have that have statement, is it actually helping me towards my goal? And I think that we can take example proofs generated by this system, or also we're experimenting with creating proofs using more sophisticated language models, Gemini and so on and so forth, and then attempting to distill this model to perform this task even more effectively than it would otherwise be able to.
So you're saying that your model will be completely reasoning in formal language?
Yes. But it will be reasoning not with formal proofs, it will be reasoning with statements, which I understand that statements are a formal language, but also, 2 + 2 = 4 is a valid formal statement and a valid informal statement. The language is meant to be as close to the typical mathematics as we can possibly muster with the Unicode system. So, yeah, that's the design philosophy. All right, let's get some cookies.